In this episode, we build a clear mental picture of orchestration, because modern Linux work often involves running many services that must stay healthy, stay connected, and update safely without constant human babysitting. When beginners first hear orchestration, it can sound like a fancy word for automation, but it is more specific than that, because it focuses on coordinating running workloads over time, not just setting things up once. The core challenge is that applications are rarely a single program anymore, and even a small service might include a web front end, an internal worker, a database connection, and a logging path, all of which must be managed together. When something crashes, the system should recover quickly, and when traffic spikes, capacity should adjust in a controlled way. Orchestration is the set of ideas that make that possible, and Kubernetes is the most common name you will hear in that space, with Docker Swarm and Docker Compose often discussed as simpler or differently scoped models. By the end, you should be able to explain the objects and the mental models without getting trapped in tool trivia. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A practical way to start is to define what orchestration is trying to solve that simple scripting cannot solve well. Scripts are great for repeating setup steps, but orchestration is about keeping a desired running state true over time in an environment where failures are normal. A process can crash, a host can reboot, a network path can flap, or a deployment can introduce a bug, and the system needs a consistent strategy for what to do next. Orchestration also helps with safe change, because teams need to roll out updates gradually, verify health, and roll back when necessary. It deals with scheduling, meaning deciding where workloads run, and it deals with service discovery, meaning helping services find each other reliably even as instances come and go. It also deals with scaling, meaning adding or removing instances without rewriting the application each time. When you think of orchestration as continuous coordination rather than one-time configuration, the topic becomes easier to reason about and more obviously connected to reliability and security. The next mental step is to separate the idea of a container from the idea of a cluster, because orchestration usually assumes you are working across multiple machines. A container is a packaged runtime environment for an application, designed to be consistent and repeatable, but a container running on one machine is still limited by that one machine's health and capacity. A cluster is a group of machines treated as one pool of resources, where workloads can be placed on any suitable node and moved when needed. Orchestration is the layer that makes a cluster usable, because it decides placement, tracks health, and replaces failed instances. This also changes how you think about failures, because a single machine failing is no longer a full outage if workloads can be rescheduled elsewhere. For Linux Plus learners, the important shift is recognizing that administration becomes more about managing desired state and policies than about logging into one server and fixing everything by hand. Kubernetes is best understood as a system built around objects, where each object represents a piece of desired state and a set of relationships to other pieces. Beginners sometimes assume Kubernetes is just a container runner, but the more accurate description is that it is a control system that continuously tries to make reality match what you declared. You describe what you want, such as how many instances should run, which network identity they should have, and how they should receive configuration, and then controllers watch the cluster and reconcile differences. This reconciliation model is central because it turns manual recovery into an automatic behavior, and it turns ad hoc changes into declared intent. It also supports consistency across environments, because the same object definitions can be applied in different clusters with predictable results. The exam-level understanding is not about memorizing every field of every object, but about recognizing that Kubernetes uses a declarative object model, and those objects are the language of orchestration. A useful anchor object for understanding Kubernetes is the pod, because it represents the smallest unit of scheduled work in the cluster model. A pod groups one or more containers that need to live together, share resources, and be managed as a single unit, which is important for cases where components must run side by side. The pod concept matters because it clarifies that the scheduler is not placing individual containers independently, it is placing pods. It also clarifies that networking and identity are often associated with the pod, so the pod becomes the unit that other services talk to, even though the containers inside can change or restart. Beginners often think they will manage containers directly, but in Kubernetes you more often manage higher-level objects that create and manage pods for you. This helps the system replace failed pods automatically, because the desired state is expressed above the pod level. When you can explain the pod as the basic scheduled unit, you have a stable foundation for understanding the rest of the object model. Deployments and replica sets are concepts that build on pods by adding the idea of controlled replication and safe updates. The simplest mental model is that you do not usually say, run this pod once, and then manually restart it when it fails. Instead, you declare that you want a certain number of identical copies, and a controller ensures that number stays true, creating new instances when old ones fail. This is what makes self-healing real, because the system is actively maintaining a target count, not passively waiting for a human. It also enables rolling updates, where new versions can be introduced gradually while old versions are removed, reducing downtime and allowing for quick rollback if health checks fail. The key beginner misunderstanding is thinking updates are always a big switch from old to new, when orchestration encourages incremental change with health awareness. For Linux plus reasoning, focus on the idea that higher-level objects manage replication and updates so you do not treat every container instance as a fragile pet. Services and networking objects are another major part of the Kubernetes mental model because they solve the problem of how clients find a workload whose individual instances come and go. If pods are ephemeral and can be replaced, then you cannot rely on a fixed address for a specific instance. A service creates a stable network identity that represents a set of matching pods, typically selected by labels, so clients can talk to the service rather than chasing individual instance addresses. This makes applications more resilient because the set of pods behind a service can change without clients needing to know. It also supports load distribution because traffic can be spread across healthy instances. Beginners sometimes interpret this as hiding complexity, but it is better seen as creating a stable contract, where the service name is the contract and the pods are implementation details. For exam depth, the important idea is that orchestration includes service discovery and stable identity, because without that, scaling and self-healing would break application connectivity. Configuration and secrets management in orchestration environments is also a key theme, because container images should not need to be rebuilt just to change a setting. Kubernetes supports the idea that application configuration should be injected at runtime through dedicated mechanisms, which keeps images reusable and reduces the risk of hard-coding sensitive values. This topic touches security directly because credentials, tokens, and keys must be handled as controlled data, not scattered through scripts or baked into images where they might leak. It also touches operations because different environments often need different configuration values, and a clean separation makes promotion from testing to production safer. Beginners sometimes assume configuration is always a file on disk edited by hand, but orchestration encourages a managed configuration model that can be versioned and audited. The core exam-ready point is that orchestration systems include ways to separate application code from environment-specific configuration, and doing so supports both stability and safer credential handling. Storage is another concept that changes significantly when you move from single-host thinking to cluster thinking, because you need a clear story for what data persists when workloads move. In a traditional server model, data might sit on a local disk, and the service depends on that disk being present. In an orchestrated cluster, a workload might restart on a different node, so you need a way to attach persistent storage that can follow the workload or be accessed consistently. Kubernetes addresses this through abstractions that describe storage needs and allow the cluster to provide or attach the appropriate storage resources. The goal is to separate the application's claim that it needs persistent data from the details of where that data physically lives. Beginners often get confused by this because they are used to thinking of disks as part of the server, but orchestration encourages thinking of storage as a service. For Linux plus depth, understand that orchestration must account for persistence because stateless and stateful workloads have different requirements and different risk profiles. Health checks and lifecycle management are also central, because orchestration relies on feedback about whether a workload is truly functioning, not merely running. A process can be alive but broken, such as stuck, unable to reach a dependency, or returning errors, and a reliable system needs a way to detect that and respond. Orchestration uses health signals to decide when to restart an instance, when to remove it from serving traffic, and when to consider an update safe to continue. This makes deployment safer because you can gate progress based on observed health rather than hope. It also improves resilience because the system can react faster than a human who notices an alert later. Beginners sometimes think of restarts as failure, but in orchestrated environments, restarts are a normal recovery mechanism and a sign that the system is designed to heal. The exam-friendly takeaway is that orchestration includes ongoing monitoring of workload health and uses that to drive automated recovery actions. Now it helps to compare Kubernetes with Docker Swarm in a mental model sense, because exams often test whether you understand differences in scope and architecture rather than which one is more popular. Docker Swarm is a clustering and orchestration approach built around the idea of services and nodes, where you define a desired number of replicas and the system schedules them across the cluster. It aims for a simpler operational experience, especially for teams already using Docker, and it provides core orchestration behaviors like replication and service discovery. The important difference is that Kubernetes has a broader, more extensible object model and an ecosystem that supports many advanced patterns, while Swarm tends to present a narrower set of primitives that can be easier to grasp initially. Beginners sometimes treat this as a competition, but a better view is that they represent different trade-offs between simplicity and breadth. For Linux Plus understanding, recognize that Swarm represents an orchestrator that manages containers across a cluster using a service model, and it sits conceptually between single-host container management and the more expansive Kubernetes ecosystem. Docker Compose is also part of the conversation, but the mental model is different, because Compose is primarily a way to define multi-container applications in a single, understandable description, often for one host or a limited environment. Compose helps you express that a web service depends on a database service, that certain ports should be exposed, and that specific volumes should be attached, all in a consistent file-based definition. This is not full cluster orchestration in the same sense as Kubernetes, but it is still valuable because it teaches the idea of describing an application as a set of cooperating services. Compose is often used in development or smaller deployments, and it can serve as a stepping stone for understanding how microservice-style applications are assembled. Beginners sometimes assume Compose and orchestration are identical, but Compose is better seen as application composition, while orchestration is cluster-level coordination, scheduling, and self-healing. For exam questions, it is useful to say that Compose describes how to run related containers together, while orchestrators manage those containers across nodes and maintain desired state over time. A final piece that ties all of this together is how orchestration changes troubleshooting and security thinking, because the place you look for a problem is often different than in a traditional server model. In a single server world, you might assume the service is broken because the server is broken, but in a cluster world, you ask whether the workload was rescheduled, whether it is failing health checks, whether it can reach dependencies through its service identity, and whether configuration or secrets were provided correctly. This also changes logging and evidence collection, because ephemeral instances can come and go, so you need a consistent way to collect and centralize logs and metrics. Security also shifts, because access controls now include who can change orchestration definitions and who can deploy new workloads, and those permissions can affect many systems at once. Beginners sometimes focus only on the container image, but orchestration policies and object definitions can be just as security relevant, because they control exposure, credentials injection, and network reachability. The exam expects you to recognize that orchestration is an environment-wide control plane, and that makes governance and least privilege critical. By the end of this episode, you should have a steady mental framework that lets you recognize orchestration concepts without needing to memorize every detail of any one platform. Kubernetes uses a declarative object model where controllers reconcile desired state with reality, and key ideas include pods as the scheduled unit, higher-level objects for replication and updates, and services for stable network identity. Orchestration also includes configuration handling, secrets handling, persistent storage considerations, and health-based lifecycle management, because reliable systems must coordinate many moving parts continuously. Docker Swarm represents a cluster orchestrator with a service-based model that emphasizes a simpler set of primitives for scheduling and replication across nodes. Docker Compose represents an application composition model that describes multiple cooperating containers, often in a single host context, and it teaches dependency thinking even when it is not full orchestration. When you can explain these mental models clearly and connect them to goals like self-healing, scaling, and controlled change, you will be prepared for Linux Plus questions that describe orchestration scenarios in practical language rather than in vendor-specific jargon.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.